The title of today's lecture is Log Structured File System. In early 90s, a new file system known as the Log Structured File System has developed. So what does this mean? It considers a file system partition as a log. Here, the log means that it take a note, it in append-only fashion. In log structured file system, everything is written in append-only manner, as if we take the log of the database systems. Log structured file system. So in log structured file system, everything is written in append only. Let me provide some motivations. At that time, the memory was getting cheaper and cheaper, so memory sizes were growing. And then the serious problem was the large performance gap between random I/O and sequential performance. An existing file system performed poorly on common workloads, and file systems were not RAID aware. So they have developed a notion of log structured file system. The objective is to transform all the writes into the sequential write. How can you write the data sequentially? So when in the normal file system, there is superblock here, there is inode table, and there comes data blocks. So when you append a data block to a certain file, you have to write a data block and you have to update the inode. The result, the random write, because you have to write one block here first and then second block here second. So there can occur big and long seek from writing 1 to writing 2. Let's change the framework of thinking. So what if we update the data at the location A0, and as a result of appending a data block to A0 position, the associated inode will be updated. Then because we have to append a new block. What if we can write the associated inode right next to the just written data block like this? Instead of making an in-place update, write the data block in the new position. Okay, then we can store the data block and then associate inode in sequential write. Of course, it is not sufficient. Even though they write the data blocks and inode all together, writing the data block at time t0 and writing the inode at time t1, then even though they are sequentially close together, because if there is time gap between these two, then the disk is going to rotate and they will lose a single revolution at least. Then they will violate the benefit of sequential write. So they have come up with the notion of segment. Okay, segment is a set of sequential writes that were written to the disk with a single unit. So be noted that segment is, well, in computer science, segment is used everywhere, in the memory, in the file system, or even data structures. Here, we use the term segment as a set of sequential write that are written to the disk with a single unit. So log structured file system maintains a memory buffer called segment, and then in the segment, they keep track of updated data blocks. Data block, updated inode, another data block, let me put the subscript here. And data block 2, inode 2, data block 3, inode 3, stuff like that. And then once this segment is all full with the data blocks and associated inode, then it issues this segment to the right. You can see the example at the end. So in this example, an application have written 4 blocks for inode J. So they have written 4 blocks. The first subscript of this array represent inode number. This is block number. Inode number, block number, inode number, and block number, and inode number, and block number within a file. So in the inode, the block, this should be 1, 2, 3, my apologies. Block 0 is recorded at A0, and block 1 is recorded at A1. Block 2 is located at A2, and block 3 is located at A3. So this is location of the associated data block on the disk. And then also the application has updated the data block on another file. This is inode K. And previously it was inode J. So in inode K, the application write another file at block 0. So the log structured file system maintains a buffer called segment and maintains all these blocks at the segment buffer. And then once segment buffer is full, then it writes it to the disk with a single unit so that they can be placed back to back in the consecutive manner in the disk and can be issued a single write. That's the concept of segment. Okay, then what is the write segment size, for example? The segment size should be 2 megabyte or 4 megabyte or 512 kilobyte or what? So what is going to be the write size for the segment? We are going to derive a simple equation to compute the segment size. Let's say that time to write, let's compute the time to write d megabyte here. Okay. So this is positioning time, and this consists of seek and rotational delay, but we are not going to get into details about that, but this is time to position the disk head. And then size of the segment divided by the peak bandwidth. This is transfer time. So total time to write a d megabyte is going to be t position plus d divided by the peak bandwidth. So that is going to be t write. Okay, so then what is effective write bandwidth? We are writing the segment, we are writing the data blocks in the segment unit. So effective bandwidth is going to be d divided by the time to write the megabyte, and then time to write the megabyte can be represented with this equation as before. Okay. So how do we determine the size of the segment? The objective, we like to make the effective bandwidth as close as possible to the sequential peak bandwidth. So let's say the sequential peak bandwidth as before was denoted as R peak. And then effective bandwidth is R effective. And then our objective is to we can establish the equation that effective bandwidth is a fraction f times R peak, and fraction is greater than 0 and f less than 1. Well, of course, f is close to 1. That's going to be very desirable, but nothing comes free. Nothing comes for free. So the equation is represented by this. Then what is the relationship between D and F? Okay, So the segment size D can be computed as simple equation like this. So the fraction times peak bandwidth times time to write a data block, T write. And then this is simple equation come up with final equation like this. So D equals F divided by F over 1 over F times R peak times T position. So if you assume that positioning time T position is 10 millisecond and peak transfer rate is 100 megabytes per second, and we'd like to achieve 90% of the peak rate, then it is going to be 0.9 times 0.1 times 100 megabytes times 0.01 seconds is going to be 9 megabytes. But this equation grows very fast as f reaches 1, right? The function f1 minus f is going to grow very fast as it reaches 1. So when f is 0.95, then this value is going to correspond to 0.1 minus 0.9 divided by 0.9. However, what if f is 0.99? Then 1 minus 0.99 divided like this. Okay, this is 10, but this is approximately 100. Okay, so to increase the efficiency by 10%, by increasing the efficiency by 10%, we need to increase the buffer size by 10x. Okay, so we have to set up an optimal point where you can meet a balance between memory size requirement and effective bandwidth. Now, inode keep changing because as the data block is written, the associated inode is placed right next to the written data block. Then how can we find where the inode is? That's the question. So the position in the interesting phenomenon of log structure file system is the position of the inodes keeps changing. Excuse me. So the inode, the data structure that contains the location of the most recent inode for a given inode number. So we introduced the data structure called inode map. This is kind of table or dictionary that says where the inode is, especially the most recent inode. So the inode map is also a data structure on the disk. So as you move around the inode contents changes. So inode map is also a data block. Inode map consists of a block, and of course the inode is changed. Then after inode contents is changed, it is also placed right next to the inode. So there is data block is updated. And then in the inode, this is file K. So the kth inode, it says that the first block of the file K is located and the position A0. Okay. So this point is updated, and then inode is placed right next to the data block. And then there comes an inode map, and the kth entry of the imap, which is the inode of the inode position of the kth inode, has been updated to A1. So a block of IMAP is also placed right next to the inode. Okay, still something is not that clear. There is why? Okay, so we write the data block D here and then place the inode right next to data block to perform a sequential write. So the position of the inode changes. So to keep track of the position of the updated inode, we introduce a data structure called IMAP, and we place this IMAP right next to the inode. Of course, IMAP consists of multiple blocks, so we are going to place the only updated block of the IMAP right next to the given inode. Then, next question. Then the position of the inode blocks keeps changing. Let's say that inode map consists of 4 blocks. This is inode map to represent, to keep track of the most recent position of the inode. Then each block 1, block 2, block 3, and block 4 of IMAP will be moved around. Then the next question is, how and where can you find the inode map? So the question keeps rising recursively. Okay. Then we come up with the new idea of checkpoint. So every data blocks, the position of the data blocks keeps changing. If a file system, let's say this is a file, and an application keeps writing the header block of the file. This is file, say this is file 1. Then on the disk, the low structure file system writes new versions of the header file in different part of the file system partition. That's the key idea of local structure file system. It does not overwrite anything. Instead, it finds the free position and write the fresh new versions of the updated data block to the new version, to the new place, and invalidate the old values and old copy of the data block. Okay, so in local structure file system, everything moves around, but to precisely identify the location of individual block, whether it can be a data block or it can be an inode block, you need to identify the updated position. Then computer system somehow should be able to locate the position of the individual inode, the individual data block, and to do that, some information has to be in the known position. That's a root ground. Okay. That's what we call checkpoint region. So checkpoint region does not change. So checkpoint region, the objective is how to find the inode map spread across the disk. So local structure file system must have fixed location on the disk to begin the file lookup. That's for sure. We do not field all the data blocks or all the inode in the fixed location, but there is single most important data structure that should be maintained at the fixed location. That is called checkpoint. That is called checkpoint region. And what does it have? It contains the pointers to the latest inode map. So, bingo. Okay. So there is a special region called checkpoint region that is designated position, and this position is written in place update. Okay. sorry, I have made a wrong impression. So in log structured file system, in log structured file system, everything is written in append only manner except one data structure, checkpoint region. Checkpoint region. However, is checkpoint region updated in place manner? So is checkpoint region updated if the checkpoint region, I said that checkpoint region contains the updated location of the inode map. Then if the inode map is updated, then checkpoint region is overwritten or updated in place only manner. The answer is no. So is checkpoint region, checkpoint region, is it updated in place manner? If there is checkpoint region version 1, then if you're going to update the checkpoint region, then does the application or does the log structure file system update in place manner like this? No. Okay. How does it do that? I'll come to the point later, but in file system partition, log structured file system maintains two regions for the checkpoint at the very end and at the very beginning. So it overrides it writes the contents of the checkpoint region in alternating fashion. First one, second one, third one, and fourth one, like this. So it comes back and forth. So even the checkpoint region, it is not updated. It is not updated in overwritten manner. Instead, it maintains a version like log structure file system do. Okay, so then how can we read a file from the disk? It comes with the first step. First, it reads the checkpoint region. By reading the checkpoint region, you will be able to find the most recent location of inode map. And then after reading the checkpoint region, it reads the inode map. Then reading the inode map, you should be able to find the location of the inode. And then reading the inode, you should be able to find the location of data block. Okay. So as you see, the process of reading a block or process of reading a file block in log structure file system is complicated. It's complicated, complex, complicated, and complex. So it means that log structure file system reading is relatively expensive. Relatively expensive. What about the sequential read? From the file, application tries to scan the database from the very beginning to the end. But if you look at the actual location of individual file blocks on the disk, due to the nature of the file system, these individual blocks may be scattered all over the disk. So for the sequential read, if you are unlucky, then in actuality it becomes a random read in the disk's point of view. So as you can easily guess, the log structure file system is optimized for write operation. Directory is a set of inode and file name path. So how does low structured file system store the directory data? Let's consider the case where we create the file foo. Okay. And then we have to update the directory inode, and then we have to update the directory entry. Also, we have to update the inode for the created file, and we have to update data blocks for created file. So when creating or writing the data blocks for a file and inode for a file, we always update or write the data blocks first. So first, we write the data blocks for a newly created file. We write the updated inode for a created file. And then we update the data blocks for the updated directory. So it contains the newly created file's name and the associated inode number. So we created file foo and its inode number is k. So the directory data block is updated accordingly. And then we write the data inode for the updated directory. And then at the very end, we have to make sure that the inode map is updated to properly reflect the newly updated location of the inodes. So we write the map table block at the very end. So this is how we update the directory. There is a very, very important concept in local structured file system. It's garbage. Local structured file system never in place updates the data blocks. It never does that. So the issue is, as a result, local structured file system leaves the older versions of the file structures all over the disk. Okay, let me give an example. First, let's say that we overwrite the data block. Here, this is inode, and this is data block, and this is inode, and this is the first block of this file. And then we update the first block of the file, and we overwrite it. And then data block is updated, and then associated inode is updated as well. So we write the newer version of the data block at the new position, and we write the newer version of the inode at the newer position as well. So these two blocks becomes completely obsolete. So this becomes garbage. What if we append the block to that original file? Okay, we write one block, data block, and associate inode. And then what you'd like to do is there is file k, and we write one block, and then we like to append another to the existing block. This is conceptual view. Conceptual view. But in reality, if you write the newly appended block somewhere, okay, then we have to record the position of the newly appended block in the inode, so inode block is updated. Okay, so we write the updated inode right next to the data block. So here there is one pointer. Okay, newly created update pointer has two pointers. Pointers for the first block and the pointers to the second block. If you look at this append operation, the first block is live. This block is live. However, the previous version of the inode block, this one is invalidated. So here, the previous version of the big inode, this becomes garbage. Garbage. Okay, so if the local structured file system does this operation over and over and over again, then because we do not utilize the existing blocks, at some point all these partitions will fall and most of them will become invalid. So we have to clean them up. What to do with the older versions of the block? In versioning file system like Waffle, this is the proprietary file system of NetApp. And what if then ZFS and BTRFS? These file systems are our versioning file system. They keep maintaining all the older versions of the file. But in local structured file system, we periodically clean the older versions of the file data, inodes, and the other structures. So this behavior and this operation is called garbage collection. This behavior is called garbage collection. The name stands for it. And then the unit of garbage collection is segment. So when performing garbage collection, we read the number of all segments from the disk. And we identify the valid blocks. We identify which of the blocks are invalid and which of them are valid. And then write the valid blocks to the new segment in memory, and then write S segments to the disk. Of course, the newly created segment number of newly created segments should be smaller than number of the cleaned segment. So this is the schematic representation of what the garbage collection is. So as we write the data block to the segment, we have to invalidate the existing version of the block by writing the new data. So if you consider segment A and segment B, then segment A, there's going to be a valid block and invalid block. This one's valid, 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 and there are 3 valid blocks in segment B. So we are running out of the space to make the free space. And then what we do is we move the valid blocks from segment A and segment B to the free segment C. We migrate the valid blocks. And after migration, we make the segment A and segment B free. To make the segment B and A free, we update the map table and stuff like that. So this is garbage collection. As a result, we free 2 segments, and we use 1 segment. So effectively, we get 1 free segment. So that's called garbage collection. Segment summary block contains the information about which block in the segment is valid, invalid, and free. So in a segment, there are 3 types of blocks. This is free, some blocks free, this is free. Oops, oh, sorry, now let me do it again, because the segment is filled from the beginning. So some block is invalid, invalid, valid, invalid, valid, and these blocks are free. Okay, so these blocks contains some data which may be invalid or valid, and these 2 blocks contains the free blocks. Okay, but when you perform the garbage collection, okay, we cannot scan individual blocks and check if the individual blocks are free or not. So in log structured file system, the segment starts with a special block called segment summary block, SSB, or SS, segment summary. Okay, so this segment summary stores the inode and then file offset for each data block in it. So for example, here the first block belongs to file K, and it means the offset of its 0th block in file K. And second block is also file K, and it is first block of the file K. Okay, this is contents of the summary block. By looking at the summary block and by comparing the contents of the IMAP and the contents of the summary block, we should be able to identify the associated data block in this segment is valid or not. Of course, it takes lots of time, because to determine whether a given block is valid or invalid or not, the original design of the log structured file system, the summary block contains the file inode number and then the block offset of the associated data block. Okay, it does not say anything about whether it is valid or invalid. To determine whether a given block is valid or invalid, file system has to look up the in-memory IMAP and then find the location of the inode K, and then find the location of block 0. Then if you navigate through the IMAP, then you should be able to find the most recent location of the block 0 of file K. So for a given segment, if you compare the entry of the summary and the value of the block location of derived from the IMAP, then you should be able to find the recency of a given data block. That's quite expensive. Expensive means, in computer science, expensive always means that it takes lots of time. Okay, so what issues do we have in garbage collection? Garbage collection is expensive because you have to select a number of segments and you have to migrate valid blocks from the old segments to new location. It causes lots of memory copy and even disk migration. So the first issue is when to clean. Shall we do it periodically? Of course, file system performs garbage collection in the background and periodically. And also it performs a garbage collection when the file system is full. And also, if it is necessary, then it detects the idle time and then performs garbage collection. This is relatively easy. However, the more important issue is which block to consolidate. There are a number of segments on the disk. Okay, so these are all used up. So some part, the 3 out of 4 is invalid, and last one is valid. Here, this is invalid, and this one is invalid and valid. And there's only one free space left, free segment left. So we have to select some of these files, some of these segments, and then migrate the data blocks to here, and then get a new segment. The easiest way is if we reduce the number of blocks that are migrated in the course of segment cleaning or garbage collection, that is going to be ideal. Okay, so in determining the victim for the garbage collection, first concept is we have to separate the hotness of a segment. Hot segment is a segment that keeps updated, and cold segment is a segment whose blocks are rarely updated. So if a segment is hot, okay, then it keeps invalidating data blocks. So at the end, if you leave the hot segment as is, at some point, all the blocks of the hot segment is going to be invalidated because most of the blocks in the hot segment has a tendency to getting updated in periodic fashion. But for the cold segment, it is not going to be cleaned or invalidated. So given this observation, in the low structure file system, hot segment, low structure file system has to clean the hot segment later and cold segment sooner. In that way, we can minimize the number of block migration, and then we can increase the efficiency of garbage collection. Efficiency here means that the number of free segments that can be obtained as a result of migrating or cleaning M segments. So we are cleaning M segments and getting N segment. Okay, then it is better if M is much larger than N. So we clean lots of segments and by using fewer number of free segments, then that is going to be more efficient. Okay, that's one of the criteria of selecting a segment victim segment for the garbage collection. what if the crash happens when the file system is, what if the crash happens when the LFS is in the middle of writing the segment to the disk? There can be two cases. Oh, sorry. First, LFS has two data structures. First one is in memory. This is in memory. And this is on disk. Local structured file system maintains a set of segments as a linked list. The order in which linked list is the order in which the segments are written to the disk. And then local structured file system LFS organize the file system partition as a log and is linked list of the segments. So this is a file system. This is a disk. This is beginning of the disk, and this is the end of the disk. And at the beginning and end, there is checkpoint region. Here, there's checkpoint, and there is another checkpoint. So there are two regions for the checkpoint. And checkpoint contains two pointers. First one is the beginning segment of the segment list, and the end segment of the segment list. So if you follow the link, and this is the beginning segment, let's number it 0, 1, 2, 3, and 4. So this is the beginning of the segment list, and this is the end of the segment list. So checkpoint region always maintains a pointer to the beginning of the segments list and then end of the segment list. Okay. Their crash can happen in two situations. First, the crash can happen while updating the checkpoint region. Or the crash can happen in the middle of writing the segment. There are two cases. So let me summarize it. The file system may crash in the middle of updating or writing the checkpoint region, and then in the middle of writing the segment to the disk. If the system crashes when there is no traffic to the disk, then no problem, because everything already has been securely written to the disk and there's no update that are currently undergoing. So that is no problem. But the problem is that the file system actively writes some data blocks to the disk, and system crashes before the file system finishes writing itself. Then what is going to happen? First one is the checkpoint region. Checkpoint region contains very important data, and they have to be always written in atomic manner. So to ensure and to avoid any corruption on the checkpoint region, they come up with this idea. First, it writes the timestamp at the beginning of the checkpoint region. It writes a timestamp first. And then it writes the checkpoint region body, which contains the location of most recent inode maps. And then once it's done, it writes a checkpoint again. Okay, so this is first checkpoint. And then in the next checkpoint, it does the same thing. Writes a timestamp at the beginning of the checkpoint region, and then write the data blocks, so inode maps on the checkpoint region, and then write the timestamp, which is the same as the timestamp of the first one to here. 1, 2, 3. When crash happens, the file system, because checkpoint region is the location, because the checkpoint region location is fixed, and the file system knows where the checkpoint regions are, when the crash happens, it reads a timestamp at the beginning of the checkpoint region and at the end of the checkpoint region. If they differ, if they do not coincide, then they ignore the contents of the checkpoint region. And then if both of the checkpoint region contains a valid checkpoint region data, then it selects the most recent one. So that means that's how log structure file system ensures the consistency and atomicity of checkpoint region update. Okay, but checkpoint region is updated in every few seconds. For example, the default is 30 seconds. Okay. So if we draw the timeline, this is checkpoint region is updated, written to this. This is the time point where checkpoint region is updated, and this is the time point where checkpoint region is written to the disk. Assume that the crash happens here. So checkpoint region was safely written to the disk, but there are lots of segments written to the disk. And then crash happens. So what is going to happen? The recovery module first reads the most written checkpoint region from the disk. And based upon the checkpoint region, it rebuild the IMAP. Rebuild means it reads the IMAP blocks from the disk and construct an in-memory IMAP table. Construct in-memory IMAP table. In-mem IMAP table. And then from the if you look at the checkpoint region, it contains the pointer to the segment, the pointer to the first beginning of the segment list. Then from this part, starting from the first segment from the list, it scans the segment list following the pointer. Okay. Then at some point, the logo structured file system, the recovery module of the logo structured file system will come to the position where the next pointer points to the segment, but this segment does not have valid segment summary area block. Okay. By looking at the segment summary, we can understand whether given segment is successfully written or not. Okay. So starting from the this is first. Starting from the first segment in the checkpoint region, it scans the valid segments following the next segment pointer and updates the inode map until it reaches the end of the list. Okay, this is how we perform crash recovery in logo structured file system. Okay, let's summarize the contents we've covered in this lecture. We have introduced a new approach to updating the disk. It is called copy and write, and all the blocks are written in append-only manner. And to expedite the process writing the data blocks to the disk, we have to gather all updates into memory, and it's called segment. The data structure is called segment. So logo structured file system is optimized for random write. This is for random write, and it works good for hard drive, parity-based RAID, or even flash-based RAIDs. So some modern commercial file system adopts a similar approach in updating the file system. It says copy on write approach. That include NetApp's Waffle, Sun's ZFS, and Linux BTRFS. So that's the end of the lecture.